This is Applied Calculus, Lesson 1.1 on functions. Our textbook begins with a review of the Cartesian coordinate system. The Cartesian coordinate system is also known as the rectangular coordinate system, and the word Cartesian comes from the mathematician René Descartes. And they ask us to recall that the Cartesian coordinate system is made up of two axes, the x-axis, which is the horizontal axis, and the y-axis, which is your vertical axis. And we use this coordinate system to plot ordered pairs. Typically, ordered pairs are x and y values, x comma y. And if we had a point, say 4 comma negative 2, that means we would go 4 to the right on the x-axis and 2 down on the y. And finally, they want us to recall that the coordinate system is divided into 4 quadrants, and we number those quadrants starting with the first quadrant in the top right corner. That is where both the x and the y-axis are positive, and we move in a counterclockwise rotation when we number. So here's quadrant 2, quadrant 3, and quadrant 4. We can graph equations in the coordinate system. Before we do, we just review that equations with one variable will have a solution of a single number, and equations of two variables will have a solution of an ordered pair. And we can use this to create a table of values and then do what's called point-by-point plotting, and then sketch a graph that connects those points. So they're asking that we generate a table of values for y equals 9 minus x squared. So we'll create a table with x and y. We choose the x values, negative 2, negative 1, 0, 1, 2. This is the independent variable because we can choose its values freely. The y is the dependent variable because for each x you choose, you must plug it into the equation, and that will give you the value for y. So values for y are dependent on values of x. So if we plug negative 2 in for x, negative 2 squared is 4, 9 minus 4 is 5, and we'll do the same for each value. 9 minus negative 1 squared is 8. And now that you have these ordered pairs, negative 2, 5, negative 1, 8, 0, 9, 1, 8, and 2, 5, we can plot them on the coordinate plane. And if we connect them, we see that this is a parabola opening down with its vertex at the point 0, 9. So definition of a function is a correspondence between two sets of elements such that to each element in the first set there corresponds one and only one element in the second set. The first set is called a domain and the second set is called a range. So the domain is typically your x values, the range your y values. And as long as you don't have more than one arrow coming from each element of the domain, you're fine. So table 1 is a function. Table 2 is a function because even though multiple arrows go to the range, each arrow only comes from the domain once. So table 2 is a function. And table 3 is not a function because we see the domain can be split to multiple values for at least one or more of its elements. And we would say this is not a function. Now we can write these ordered pairs as 0, 0, Then we have 1, 1, and 1, negative 1. And then we have 4, 2, and 4, negative 2. And then we have 9, 3, and 9, negative 3. When you see the x values being used multiple times, it is not a function, and we simply call it a relation. If an equation in two variables gets exactly one output value for the dependent variable for each input value, then the equation specifies a function. The graph of such a function is just the graph of the specifying equation. If we get more than one output for a given input, the equation does not specify a function. So, example 2 asks to determine which of the following equations specify a function with the independent variable x. So for example A, we can rewrite this. For A equals 3x plus 8, y equals 3/4 x plus 2. So we've solved for the equation and y equals 4. This is a linear equation. If we were to graph it, we would start at 2 and then use the slope 3/4 to get additional points. And an easy way to determine if this is a function is through what's called a vertical line test. If a vertical line only touches the function once, no matter where you slide it in the domain, then it is a function. So if we solve example B for y, we see we get y squared equals x squared plus 9. If we take the square root of both sides, y is equal to plus or minus the square root of x squared plus 9. And that means that we're going to get two different y values for each x value. So let's create a table of values. If I plug in negative 1, that would give me 1 plus 9 is 10, so it would be the square root of 10, or the negative square root of 10, so plus or minus square root of 10. There's two answers there. If I plug in negative 2, I would get plus or minus the square root of 13. If I plugged in 0, I would get plus or minus the square root of 9. And if I take the square root of 10, that's about 3.16. So at negative 1, I have positive 3.16, and I have negative 3.16. At negative 2, I have positive 3.6 and negative 3.6. And at 0, I have positive 3 and negative 3. So we see that this is not a function, because if I take my vertical line, I see my vertical line intersects multiple points wherever I place it in the domain. So it's hitting the graph twice, twice, twice. But it only needs to do that one time to disqualify it as a function. If you can only find one point where it hits two separate points, or I should say one element of the domain where it intersects 2 points, then it is a relation and not a function. So linear functions are often written in the form f of x equals 3x minus 7, where f is the name of the function and x is the independent variable. This is exactly the same thing as y equals 3x minus 7. We've just changed the name of y to a function name instead of a variable name. You can call it g of x, you can call it p of x, and that gives us a very useful tool where we don't have a bunch of y's that we're graphing in an equation. So if I had multiple graphs and one of them was f of x and another one was g of x, it gives me an easy way to determine which graph belongs to which function because they're labeled differently, and then we can find intersection points or whatever the point of interest of the problem is. So we're using function notation to evaluate functions, and we see they've defined a function f of x, g of x, and h of x. So to use this notation, we simply look at the question. It says f of 6. That means find the f of x function and replace all x's with the value 6. So f of 6 would equal 12 divided by parentheses 6 minus 2, which is 12 divided by 4, which is 3. We can say that f of 6 equals 3. For question B, they're asking for g of negative 2. We find the g function, which is 1 minus x squared, but we're going to replace x with negative 2 squared. This is 1 minus 4. G of negative 2 is equal to negative 3. Part C asks for h of negative 2. H of negative 2 will equal the square root of negative 2 minus 1. H of negative 2 will equal the square root of negative 3. This is not a real result. This is an imaginary number. Anytime you have the square root of a negative, that results in an imaginary number. Example 4 asks that we find the domains of our functions. So f of x equals 12 over x minus 2. And we say, well, the domain is everywhere the function is defined. The function is a fraction, so we cannot have 0 in the denominator. So that means that x cannot be equal to 2, because if it were, you would get 2 minus 2, which is 0 in the denominator. That being said, domain is all real numbers except x equal to 2. Or you can simply say domain is x not equal to 2. Both mean the same thing. Both are correct. The second one is the preferred way to express it. The first one gives you a verbal description of what the second notation is saying. For g of x, you have 1 minus x squared, and you say, well, is there any value that makes this expression undefined? And we're allowed to subtract positives and subtract negatives. So for this one, there's no value for x that would cause a problem. We would say the domain is all real numbers. Or we could say the domain is x belongs to the set of real numbers. This is the preferred way to write the answer. And the first one is the description that gives us meaning to that symbolic notation. So next we have h of x. And because this is a square root, we know that x minus 1 is allowed to be equal to 0, or x minus 1 must be greater than 0. So we see that it is equal to 0 when x is 1. We see that it is greater than 0 when x is greater than 1. So for h of x, the domain is x greater than or equal to 1. And part D combines all of these functions. So we would say that the domain is the combination of all three of these, or the intersection of all three of these. And we see that for part D, x is greater than or equal to 1, and x is not equal to 2. In addition to evaluating functions at specific numbers, it is important to be able to evaluate functions at expressions which involve one or more variables, for example, the difference quotient. This is studied extensively in calculus, and example 6 is going to walk us through the stages for evaluating the difference quotient. So given a function f of x equal to x squared minus 2x plus 7, we can evaluate f of a, and that simply means replace all x variables with a. So part A will give us the result. F of a is equal to a squared minus 2a plus 7. Part B says replace all x variables with a plus h. So f of a plus h will equal a plus h in parentheses squared minus 2 times a plus h plus 7. We can simplify this further by foiling, using distributive property, on the binomial a plus h to expand this term, and then distributing the negative 2 through the second a plus h. This will get us a squared plus 2ah plus h squared minus 2a minus 2h plus 7. And this is the result for part B. Part C asks that we take f of a plus h and subtract f of a. So we're going to take our answers from part B and subtract the answer from part A. So we see that a squared minus a squared cancels. We have a negative 2a, and we're going to subtract a negative 2a, so that double negative turns into a plus, and they cancel. And we have 7 minus 7, so they cancel. So part C leaves us with 2ah plus h squared minus 2h. Finally, part D asks us to use the entire difference quotient, which is saying take the result from part C and put it in the numerator and put h in the denominator. Because we see that there is an h term, or an h in all three of these terms, we can factor it out using GCF factoring. And that'll give us an h times 2a plus h minus 2. And now this h cancels with the denominator, and we're left with f of a plus h minus f of a over h is equal to 2a plus h minus 2. That is our difference quotient for the function f of x. So an application we can look at now is called break-even analysis or profit-loss analysis. And this will return the number of times. So an application we'll now look at is called break-even analysis or profit-loss analysis. We will come back to this topic throughout the book. Any manufacturing company has costs, costs and revenues. The company will have a loss if the revenue is less than its costs. It will break even if the revenue is equal to its costs, and it'll have a profit if the revenue is greater than its costs. The costs include fixed costs such as the plant overhead, product design, setup, and promotion. And it'll also have variable costs, which are dependent on the number of items that are being produced at a certain cost per item. In addition, there is a price demand function, usually established by the financial departments, that uses historical data or sampling techniques. They play an important part in the profit loss analysis. We will let X be the number of units manufactured and sold and represent the independent variable. And the cost function, the revenue function, and the profit function, along with the price demand functions, are often stated in the following forms, where A, B, M, and N are constants determined from the context of the problem. So cost function is fixed cost plus variable cost. Variable cost will have the variable X attached to it, and the constant A is the fixed cost. The price demand function is going to be P equals M minus NX. This is often determined by the financial departments. We will be able to determine this using regression analysis and historical data. But often it will be given to us in a problem. The revenue function is going to be the price demand function P, that's what this P is here, times X, which is the number of items sold. And profit is a capital P, where the price demand is a lowercase p. So capital P of X is equal to the revenue minus the cost. But remember, the revenue we've just defined as X, the number of items, times P, the price per item from the price demand function. So here in example 7, it says a manufacturer of a popular digital camera wholesales the camera to retail outlets throughout the United States. Using statistical methods, the financial department in the company produced the price demand data in table 4, where little p is the wholesale price per camera at which X million cameras are sold. So notice that X is counted in millions. Notice as the price goes down, the number sold goes up. So if you're given just this table, it would be up to us to come up with the price demand function using regression analysis. However, they have given us the price demand function here. So let's use some regression analysis so that you know the technique that's needed, and you can see that the answer will be the same that the book has given us. So in our calculator, we can go to the Stat button. The first option is Edit. I'll hit Enter. And we see list 1, list 2, list 3. We're going to use list 1 for x values. We're going to use list 2 for y values, which is our price demand values. So for list 1, we're going to enter 2, 5, 8, and 12. So 2, enter, 5, enter, 8, enter, and 12. Enter. So now I hit the right arrow to go to the next column, and I'll put in the dependent values, 87, 68, hit enter, 53, and 37. So now that we have our historical data in here, we can go back to Stat, hit the right arrow to choose the Calc menu, and then we're going to look for a linear regression model. So we're going to come down to option 4, enter. The X list is from list 1, the Y list is from list 2, that's correct. We go all the way down and highlight the word calculate, we hit enter, and we see that we get our A value. Notice that A is next to X in the calculator's template, is negative 4.96. Well, notice next to the X is negative 5. So if they rounded this to the nearest tenth, it would have given us negative 5x. Let's round B to the nearest tenth, and we get 94.8. And we see 94.8 is what they have. So we were able to generate the B value, which is the constant according to the calculator's template, and the A value, which is the slope according to the calculator's template. And we now have a linear regression equation that models our data here. So part A says plot the data in table 4 and sketch the graph of the price demand function. We can do this now. So on our calculators, second, and stat plot is in blue. We're going to choose plot number 1. Make sure that the option on is selected and hit enter. We come down and we choose the type of plot we want, and we want to plot the points here. So that's the first one, the scatter plot. Make sure that's highlighted and hit enter. Make sure it says where you get your X and Y values from, list 1 and list 2. Those are correct. And then you can choose what type of dot you want on your graph. The easiest to see is the square. And we can hit graph, and we don't see anything. So in the zoom button, you hit zoom, and you go down until you see stat plot. Zoom stat, that means it'll zoom in on where your statistics points are, so option 9, and we see there's our plot. Now they wanted us to also plot this price demand function, so we go to y equals, and we type in 94.8 minus 5x, you hit the variable key, we hit enter, and now when we hit graph, it draws our price demand function in there. Remember, this is a model that we calculated to fit the data, and we see that it doesn't hit any of the points exactly, but it stays in between them very well to fit all of the data to the best possible line, and that's known as the line of best fit. So now, part B, what is the company's revenue function for this camera? Well, we can do that. The revenue function so that's going to be X times P, but we have a function for P, so it's X times 94.8 minus 5X, or we can say the revenue function is 94.8X minus 5X squared. Part C says complete the table computing the revenues to the nearest millions of dollars. So here's table 5. We have these X values that we have to plug into R of X and generate those points. So we can go to our function here and say 94.8x minus 5x squared. And now we can go to our table, and for under table setup, we're going to start, well, the start's not that important. It's the independent we want set to ask. That means we will type in which x values we want, but the dependent we want set to auto. That means it will use the equation for r of x that we just put into the y of the calculator to calculate the output values. And now when I go to table, we have all of our answers here. I had typed these in advance. Because I have it set to ask, there's nothing here. You would type in each x value and it calculates the y value as you do that. And that y value is coming from the equation we put into y1. Okay, so part C says complete table 5, computing revenues to the nearest millions of dollars. This is part C right here. Part D says plot the data in table 5, then sketch the graph of the revenue function using these points. And then part E says plot the revenue function. So we're going to do all of this on the graphing calculator now. So we're going to take this table of values and put it into our stat plot. So we hit the stat button. We go to edit. We're going to delete these values out. And we're going to enter the table that we created for our revenue function. So 1, 3, 6, 9, 12, and 15. And now we'll put the revenue values in. And we have the revenue function for y. So we're going to go to zoom, and we're going to say do the stat zoom so that we know it's going to fit our data points in. So zoom stat is option 9. And there's our data points, and there's our revenue function, and we've plotted them together. So we see that these points fit the line, and you have to remember we generated these points from our function, where in the beginning we plotted historical data and generated a linear price demand function. It didn't fit exact, but it was the line of best fit. These points land on the line because these points were generated by the function that we're graphing. So this is the end of this lesson. Rewatch the video, use the guided notes, complete the homework practice problems, and come to next class with questions.